We'll now look at numbers that are known as complex numbers. And in order to do this, we have to define a particular type of number. We define this imaginary unit I such that I squared is equal to -1. And this is how we're going to define the complex numbers. The complex numbers are anything that can be written in this form, a plus bi, where a and b are real numbers. For example, 2 plus 8i, or 4 minus 7i. We could also have something like 0 plus 6i, which we tend to just write as 6i. And so these are the complex numbers. And real numbers are also complex. For instance, 12 plus 0i is the same thing as 12. We'll now look at how to add these. So if we have this problem, 7 minus 8i plus -1 plus 6i, I can start by ignoring these parentheses. The order of addition doesn't matter. So I have 7 minus 8i minus 1 minus 6i. I know that 7 minus 1 is 6. And then from there I can combine these the same way I dealt with polynomials. -8i and -6i are like terms. -8 minus 6 is -14i. So my sum is 6 minus 14i. Next we'll look at subtraction. 7 minus 2i minus 5 minus 8i. The first step in subtraction is to distribute the negative sign. I get -5 plus 8i. And now I can do this the same way I dealt with addition. I have 7 minus 5 is 2. -2i plus 8i would be 6i. Multiplication also works very similarly to how it did in polynomials. We're going to FOIL. The first terms, 5 times 1 is 5. The outside terms, 5 times 3i is 15i. The inner terms, 8i times 1 is 8i. And then my outer terms, 8i times 3i is 24i squared. And here it's important to remember that I squared is equal to -1. This is how we define this term. So this is 5 plus 15i plus 8i minus 24. I can combine the 5 and minus 24 to get minus 19. And then 15i plus 8i is going to be 23i. So I have -19 plus 23i. Imaginary numbers also have this term called the conjugate. So if I have an imaginary number that I'm going to call z, that we know is written as a plus bi, then the conjugate we denote by the z bar. And it's given by a minus bi. In short, we find the conjugate of an imaginary number by changing the sign on the imaginary part. We'll do this example where we want to multiply -5 plus 7i by its conjugate. Like we said in the last one, that -5 plus 7i has a conjugate of -5 minus 7i. It just comes from changing the sign on the imaginary part. Now we can FOIL. -5 times -5 is 25. My outside two terms, -5 times -7i, would be plus 35i. The inside two terms, 7i minus 5i, or times -5i is -35i. The last two terms, 7i times -7i would be -49i squared. We can see that this 35i and -35i are going to cancel. Since I squared is -1, this becomes 25 plus 49, which gives us 74. We can see that we got rid of our imaginary unit I. And in general, that's going to be true. In general, a plus bi times a minus bi comes from squaring a plus b squared. So now we have this nice shortcut formula to use when we multiply conjugates. Let's consider this, 1 over negative 1 plus 2i. We tend to like these written in the standard form, a plus bi. The fact that the a is on the denominator isn't in the natural order of things. So in order to get rid of it, we multiply by the conjugate. And if we multiply the top, we need to multiply the bottom. So we're going to multiply by 1 using this conjugate. On the top, I just have negative 1 minus 2i. On the bottom, using our shortcut, we can square the first number, which is negative 1 squared, gives us 1, plus squaring the second number. 2 squared is 4. We know that 1 plus 4 is equal to 5. So when we write this in standard form, we have negative 1 over 5 minus 2 over 5i. So now we can easily see the a plus bi form. Let's consider this one where we're dividing these complex numbers. And we're going to do this the same way we did the last example. We'll multiply by the conjugate of the denominator, both the top and the bottom, by this number. When we multiply the top, we do need to FOIL. The first terms, 2 times negative 6, gives me negative 12. The outside two terms, 2 times negative 8i, is negative 16i. My inside terms, 6i times negative 6i, is negative 36i. And my last two terms, 6i times negative 8i, would be negative 48i squared. On the denominator, we can use the shortcut where we square the first term plus square the second term. And now we can simplify. This is negative 12. Negative 16 minus 36 would be negative 52, so we have negative 52i. And since I squared is negative 1, this becomes plus 48. All over 36 plus 64, which is 100. We can combine the 48 and the negative 12 to get 36 minus 52i over 100. After that, we could break it up to 36 over 100 minus 52 over 100i. And we can reduce those fractions. 36 and 100 have a 4 in common. That would give us 9 over 25. And 52 over 100, well, those also have a 4 in common to give us 13 over 25i. The last thing we'll look at here are the powers of I. So we know that I is of course equal to itself, and we defined I squared to be equal to negative 1. If I try to do I cubed, well, this is the same thing as I times I squared. So I times negative 1, which is negative I. I to the fourth is the same thing as I times I cubed, and we know I cubed is negative I times I, would be negative I squared, which is negative negative 1, which is 1. If I continue, I to the fifth can be written as I times I to the fourth, so 1 times I is I. I to the sixth is I times I to the fifth. Well, I to the fifth is I, so now I have I times I, which is negative 1. I to the seventh is I times I to the sixth, so negative 1 times I gives me negative I. I to the eighth is I times I to the seventh. I to the seventh is negative I, so now I have negative I squared, which is 1. So we see this pattern, and overall the powers of I are going to repeat between I, negative 1, negative I, and 1. And this will allow us to take very high powers of I very easily. we start with I to the 31. And the key is to write this in terms of 4. So we know that 31 divided by 4 is 7 with a remainder of 3. So I can rewrite this as I to the 4th to the 7th times I cubed. And we can double check this using our rules of exponents. 4 times 7 is 28, plus 3 is 31. I to the 4th is 1, so this is 1 to the 7th, times I cubed, which was negative I. So we just get that this is negative I. We'll look at one more, I to the 105. Well, if I do 105 divided by 4, I get that the quotient is 26 with the remainder of 1. So I can rewrite this as I to the 4th to the 26th power times I. I to the 4th is 1. And then 1 to the 26th power is 1 times I, which is I. So now we can see that we can very easily compute these powers by converting them to something in terms of the power of 4 and then our remainder.